Hello and welcome to the SysGuides YouTube channel. Today we are going to talk about something that powers the entire internet, yet most people do not really think about: DNS. And trust me, this small tweak in your Linux system can make a big difference in your internet experience. Now, you might be wondering, DNS? That sounds technical, maybe even boring. Or you might be thinking, wait, is this about setting up a full DNS server with all those complicated records like AE, MX, and CNAME? No, don't worry. We are not diving into that level of complexity today. Instead, we are going to focus on something super practical: how a few simple changes in your Linux DNS settings can give you a faster, more private, and even more secure browsing experience. This video is not filled with hardcore Linux jargon. It is designed for everyday Linux users, whether you are using Fedora, Ubuntu, Arch, or any other distro. And yes, if you are an expert watching this, you will still find some useful tips. And here's what we're going to cover in this video. First, we'll see why DNS plays such an important role in both speed and privacy. Then I'll show you how to switch to trusted providers like Google, Cloudflare, and Quad9. We'll also set up DNS-over-TLS and DNS-over-HTTPS, and even enable DNSSEC so your DNS queries stay private and tamper-proof. Finally, we'll test and verify the setup with TCP dump to make sure all these protections are working and there are no DNS leaks. Sounds good? Awesome. Let us start from the very beginning and understand why DNS is so important. So, what exactly is DNS? DNS stands for Domain Name System. You can think of it like the phone book of the internet. When you type a website like example.com into your browser, your computer does not actually understand that name. What it really understands are numbers. Something like 23.215.0.138. That is the IP address of the server. Now, remembering numbers like that for every single website would be nearly impossible, right? So, DNS comes in and makes our life easier. It is the system that translates these human-friendly names into the actual IP addresses that computers use. And all of this happens in just milliseconds. It happens every single time you visit a new website. So if your DNS is slow, your entire internet experience will feel slow. And here is the interesting part. By default, your system probably uses your ISP's DNS servers. They work, sure, but they are not always the fastest, and many times they do not care about your privacy. That is why switching DNS to a trusted and faster provider can make a huge difference. Now that you understand what DNS does, let us talk about privacy and security. Traditional DNS, the one we just talked about, has one big problem: it is not encrypted. That means anyone on your network, your ISP, hackers, or even someone sitting next to you on public Wi-Fi can see which websites you are visiting. And worse, they can tamper with your DNS queries and trick you into visiting fake websites. That is where encrypted DNS protocols come in. Let me explain the three big ones you need to know. First, DNS-over-TLS, also called DoT. This uses TLS encryption, the very same technology that secures websites when you see HTTPS in your browser. It creates a private and secure tunnel just for DNS queries using port 853, unlike regular DNS, which defaults to port 53 and remains unencrypted. That means no one can spy on your DNS traffic while it is moving across the internet. Think of DNS over TLS as sending a letter in a locked box through a special courier who travels on a clearly marked DNS-only route. The box is secure, and no one can read the letter inside, but everyone can see it's a DNS delivery. Here in the output, you can see a minus sign in front of DNS over TLS. That simply means this machine does not have DNS over TLS enabled right now. Second, DNS over HTTPS, or DoH. This one is not shown here in the system output because it usually lives inside your web browser. Although it can also be set for system-wide use, it is generally better to use only one method across the whole system, and the recommended one is DNS over TLS. DNS over HTTPS is best left for browsers, and many of them already support it. So how does DNS over HTTPS actually work? Instead of using a dedicated port like DNS over TLS, it hides DNS queries inside normal HTTPS traffic. That way, to anyone watching, it looks exactly the same as your everyday web browsing. It is still fully encrypted, but it blends in with all the other HTTPS connections, which makes it harder to block or filter. For DNS over HTTPS, think of sending a locked box, but slipping it into a big bag of regular mail delivered on the standard route. That's port 443. The box is still locked, just like with DNS over TLS, but now it blends in with everyone else's packages. And then there is DNSSEC. This one is a little different. It does not encrypt your traffic. Instead, it adds authenticity. It lets your computer verify that the DNS response you received is genuine and that no one has tampered with it along the way. So even if someone tries to redirect you to a fake website, DNSSEC can catch it. Think of it like this. If DNS over TLS is a locked box, and DNS over HTTPS is that same locked box hidden inside a regular envelope, then DNSSEC is like putting a wax seal or a signature on the box itself. Even if someone tries to copy it, your computer will know the seal is missing or broken. So remember this, DNS over TLS and DNS over HTTPS keep your DNS private, while DNSSEC makes sure it's authentic. When you combine them, you get privacy, speed, and strong protection against tampering. But as you can see here, DNSSEC is not enabled yet. I'll be turning it on shortly, along with DNS over TLS and DNS over HTTPS. You will also see default route, LLMNR, and MDNS in the output. Default route determines if this interface is used for internet lookups. LLMNR and MDNS are both for finding devices on your local network, like printers or other computers. These are only about local network resolution and aren't really important for this video since we're focusing on configuring public DNS servers. All right, now that you have a clear idea of what DNS is, why we might want to change it, and the different encryption options, let us move on and actually explore some public DNS providers. There are quite a few out there, but today I want to highlight 3 of the most important ones: Google Public DNS, Cloudflare DNS, and Quad9 DNS. These 3 are often ranked among the very best when it comes to speed, security, and privacy. So, let us begin with the first one, and this is a big one: Google Public DNS. Google launched this service way back in 2009. The whole idea was to make the web faster and more secure for everyone. They provide it as a free global DNS service with a heavy focus on speed, reliability, and strict compliance with DNS standards. So these are the IPv4 and IPv6 addresses for Google Public DNS. Now let us look at the key features. Google Public DNS is one of the oldest and most widely used DNS resolvers. It is backed by Google's massive infrastructure and a global Anycast network. What that means is, when you send a query, it is routed to the closest available server, and that gives you excellent speed and worldwide reliability. It also supports modern encryption standards like DNS over HTTPS and DNS over TLS, so the resolution stays private. And it validates DNSSEC, so every response is cryptographically verified, preventing spoofing and blocking those nasty cache poisoning attacks. When you query an invalid domain, it gives a clean NX domain response. That means non-existent domain, without any kind of redirection to sneaky search pages or ads. Now, as far as trade-offs are concerned, the main issue with Google Public DNS is that it does log queries for performance and security analysis, and that definitely raises privacy concerns for many users. Google does say that this data is not used for targeted advertising, which is somewhat reassuring, but still, privacy remains a concern for some people. Another limitation is that it does not include any built-in malware or content filtering. So while it is fast, it is reliable, and it is technically very strong, the compromise comes at the cost of privacy. Next, we have Cloudflare DNS. This service was launched in 2018, and it quickly became very popular. The main reasons are speed and privacy. Cloudflare actually claims to be the fastest DNS resolver in the world, and independent tests often agree with that. But here's the thing, Cloudflare is not only about speed, they also focus heavily on privacy. They promise that user data will never be sold or used for advertising. To prove that promise, Cloudflare even brings in independent auditors. These audits are done every year just to confirm that the policy is real and not marketing talk. Cloudflare also gives you some options. There is the standard setup, which is fast and private. Then there is Cloudflare for families. That one comes in 2 versions. One version blocks malware, the other version blocks malware and adult content together. So depending on your needs, you can simply choose the level of protection that works best for you. And these are the IPv4 and IPv6 addresses of Cloudflare DNS. As for the key features, here's what Cloudflare DNS offers. Like I said earlier, Cloudflare DNS has a strong focus on privacy, and it promises not to log your IP address. Cloudflare also uses anycast routing, but instead of big centralized data centers like Google, it runs a massive edge network with servers in hundreds of cities worldwide. This design helps it deliver very fast performance, often matching Google. They support DNS-over-HTTPS, DNS-over-TLS, and DNSSEC validation. They return proper NX domain responses without hijacking, just like Google DNS. And when configured correctly, the risk of DNS leaks is also very low. Cloudflare also provides filtering variants, where one blocks malware and another blocks both malware and adult content. While Cloudflare DNS is fast and privacy-focused, there are a few trade-offs. You still have to trust their privacy promises, since all your DNS queries go through their network. There's limited customization beyond the basic filtering options, and in some regions, other DNS providers might be even faster. And finally, we have Quad9 DNS. Quad9 officially launched in 2017. Unlike Google or Cloudflare, it is not run by a big tech company. It is operated by the Quad9 Foundation, a nonprofit based in Switzerland. Their mission is simple: security and privacy first. Now let us take a look at Quad9's DNS addresses. They offer both IPv4 and IPv6 options. And as for the key features, here's what Quad9 DNS offers. Quad9 takes a very different approach. Instead of relying on a single company's filter list, it pulls threat intelligence from dozens of global cybersecurity partners. That means when new phishing campaigns, malware domains, or ransomware sites appear, Quad9 can start blocking them almost immediately. For example, imagine you click on a link to a brand new ransomware site. If one of Quad9's partners has already flagged it, your DNS request is blocked before the site even loads. That is something Google DNS does not provide at all. Cloudflare does have its families option, but Quad9 goes further by combining intelligence from many different sources worldwide. Another big difference is privacy. Quad9 does not log or process your IP address, and it is fully GDPR compliant. In short, your browsing habits are not being tracked or monetized. Just like Google and Cloudflare, Quad9 supports modern standards such as DNS-over-HTTPS, DNS-over-TLS, and DNSSEC. It also gives correct NX domain responses without hijacking them. But the real difference is that Quad9 is run as a nonprofit, and its security filters come from a wide network of partners. That makes it more community-driven compared to Google and Cloudflare. And what about the trade-offs? The first one is performance. Quad9 does not have the same massive network as Google or Cloudflare, so speed can vary depending on where you live. If you happen to be close to one of their regional servers, then performance will be great. Otherwise, it may feel slower. What makes Quad9 unique is its mission. It is a nonprofit foundation based in Switzerland, a country known for strong privacy laws. Unlike big tech DNS providers, Quad9 is not trying to monetize your data. Its only goal is to protect users and make the internet safer. Compared to Google and Cloudflare, Quad9 might not always be the fastest, but its strength is unmatched threat intelligence. With dozens of global partners feeding it data, you get real-time protection that updates faster than most security software. So if your priority is security, transparency, and a provider that aligns with privacy-first values, Quad9 is an excellent choice. All right, that wraps up our overview and comparison of the major public DNS providers. Now, let me show you how to actually add one of these DNS IP addresses to our Linux system and see it in action. So open the terminal and run the command resolve control status. As you can see here, my current DNS server is 192.168.1.1. This is actually the IP address of my router. It is also the gateway to the internet. Here, the router takes care of DNS for me and then forwards the queries either to my ISP's DNS servers or to whichever servers it's been set up to use. For this demo, I will change it to Quad9 DNS because Quad9 focuses on privacy and also blocks connections to known malicious websites. But you do not have to stick with Quad9. You can use any other DNS provider you prefer. The setup steps are exactly the same. Also, DNS-over-TLS and DNSSEC are not enabled yet, so we will set those up as well. So open Settings from the top right system menu, then go to Network and open your connection settings. Under the IPv4 tab, you will find the DNS section where you can enter your servers. I'm using Fedora 42 with GNOME, so the screens may look a little different if you are on another desktop environment, but the general idea is the same. You just need to find the network settings and edit the DNS section. Make sure the automatic DNS option is disabled. Then enter the IPv4 addresses of Quad9. If you are setting up a different DNS provider, just replace these with their IP addresses. Next, click on the IPv6 tab. Disable the automatic DNS option, and enter the IPv6 addresses of Quad9. But if you are using a different provider, enter their IPv6 addresses here instead. Finally, click the Apply button. Now let us check again with Resolve Control Status. And as you can see, the DNS servers have been updated to Quad9. Just because the IPv6 addresses appear here doesn't mean your system supports IPv6. Before you continue, make sure IPv6 is actually working on your system. So open a web browser and go to the website testipv6.com. Let it run the check. And here it says no IPv6 address detected. That usually means either your ISP does not support IPv6 or IPv6 is disabled in your router. So I will open my router configuration page. To do that, I type my router's address. You should enter yours. As you can see here, in my router's configuration, only IPv4 is enabled. I will switch this to IPv4, IPv6 dual stack. Depending on your router, it may be worded differently or appear in another place, so you might need to check your router's manual. I will click OK, and it will take a little time to apply the changes, usually just a few seconds, so be patient. Now I'll refresh the page so the test runs again. And now the score is 10 out of 10. IPv6 has been detected. If your ISP or your router does not support IPv6, do not worry. IPv4 alone is perfectly fine and fully supported everywhere. IPv6 just adds extra future-proofing and some efficiency benefits, but IPv4 by itself is sufficient for all normal usage. All right, now that the IP addresses of the Quad9 public DNS servers are set, let us go into Firefox settings to enable DNS over HTTPS. Open the menu, go to Settings, then click on Privacy and Security on the left side. Scroll all the way down to the bottom and you will see the DNS over HTTPS section. Here, you can see that DNS over HTTPS is presently not enabled. You will also see 3 protection level options: default protection, increased protection, and max protection. Default protection means Firefox decides when to use secure DNS. It will use secure DNS where it is available, but it can fall back to your system DNS if there is a problem. It may also turn off secure DNS if a VPN parental control or enterprise policy is active. Increased protection means you control when to use secure DNS and choose your provider. Firefox will use the provider you select, and it will only fall back to system DNS if there is a problem with the secure DNS. Max protection means Firefox will always use secure DNS. If secure DNS is not available, Firefox will show a warning. Sites may not load until secure DNS is working again. Because I want maximum privacy and security, I will choose max protection. This ensures that Firefox will always use secure DNS and never silently fall back to the system resolver. Now, in the Choose Provider section, you can see that the default provider is Cloudflare. We are not going to use that. Instead, we will set to Quad9. So I will select Custom option. Here, you should enter the URI address of the endpoint for Quad9's DNS service, which is HTTPS DNS.quad9.net/DNS query. Once that is entered, press Enter to confirm. And now, as you can see, DNS-over-HTTPS is active, and the provider is set to Quad9. That is it. DNS-over-HTTPS has now been enabled in Firefox. If you are using a different browser, the steps are almost the same. Go to the privacy or security settings, look for DNS-over-HTTPS, enable it, and then enter the custom URI address of the endpoint for your provider. You successfully enabled DNS-over-HTTPS in Firefox, which is great if you only care about the browser, but what about everything else on your system? Applications, command line tools, background services, and even VPN connections still use the system's default DNS, which is unencrypted. To protect all of these, we need system-wide DNS security. This is where DNS-over-TLS comes in. By enabling DNS-over-TLS, we encrypt every DNS lookup from the operating system to the DNS provider. And by enabling DNSSEC, we make sure that DNS responses are validated and tamper-proof. Together, this gives protection for all DNS traffic from the machine, not just your browser. So let's go ahead and set that up next. On Fedora, Ubuntu, and many other modern Linux distributions, the service that handles DNS lookups is called systemd resolved. It comes built right into systemd. On some distributions like Arch, it may not be enabled out of the box, but you can enable it with one command. The main configuration file for this service is called resolved.conf, located inside the /etc/systemd directory. This is the file we are going to edit to enable DNS-over-TLS and DNSSEC system-wide. First, DNS. Normally, this is where you would enter the IP addresses of the DNS servers you want to use, but I have already set those in network settings, so it would be redundant here. I will just remove this line. Next, fallback DNS. This option provides backup DNS servers in case your primary ones fail. I am leaving it empty on purpose. By doing this, I make sure there are no automatic fallbacks to other DNS providers. I want my system to always use the Quad9 servers that I configured. If you skip this line entirely, systemd resolved may try to fall back to providers like Cloudflare, Google, or Quad9 by default. By leaving it empty, I am disabling that behavior. Now, DNS-over-TLS set to yes. This tells systemd resolved to use DNS-over-TLS globally. That means all DNS lookups will be encrypted when the upstream servers support it. Then is DNSSEC. If you set it to yes, that means strict DNSSEC validation everywhere. Any DNS server that does not support DNSSEC will have its responses rejected if validation fails. This is the most secure option. But here is the important warning. On Fedora 42, systemd resolved does support DNSSEC, but it is not perfect yet. Fedora actually ships with DNSSEC disabled by default because of compatibility issues. On some networks, or with some upstream DNS providers, enabling strict DNSSEC can cause certain domains to fail to resolve. That is why many people recommend using allow downgrade instead of yes. With allow downgrade, systemd resolve D will validate with DNSSEC whenever possible, but if the upstream server does not support it, it will fall back gracefully. In my case, I am using Quad9 as my DNS provider. Quad9 fully supports DNSSEC validation. That means it is safe for me to go with the strict yes option. But if you are using a different provider or an ISP that does not handle DNSSEC properly, then you might be safer choosing allow downgrade. Next is domains. This one has a very simple purpose. It tells systemd resolve D to send all DNS requests through the trusted servers we have set here, no matter what network we connect to. Without this, a Wi-Fi network or an ISP could try to override your DNS settings and push their own servers. By adding ~+ here, we make sure our chosen secure DNS provider always takes priority. And the last option is cache set to yes. This enables local caching inside systemd resolve D, so repeated lookups are faster and there is less traffic sent upstream. And this completes the configuration. Save the file and exit. Now restart the systemd network D service. And then restart the systemd resolve D service. Finally, check the DNS resolve status with the resolve control status command. As you can see, DNS-over-TLS is now enabled and DNSSEC is also enabled. And that is it. Your system is now fully secured with Quad9 DNS and system-wide encrypted DNS resolution. All right, so we've finished setting up Quad9 DNS system-wide with DNS-over-TLS and DNSSEC. But how do we know that all this is actually working? It's not enough to just configure, we need to verify. So next, I'll run a few tests to confirm whether DNS-over-HTTPS, DNS-over-TLS, and DNSSEC are really being used, and also make sure there are no DNS leaks. For this, I'll be using TCP-dump to capture DNS traffic directly from the network interface. I'll run the same capture command for each test, and then analyze the output with the help of an AI assistant to confirm what's happening. We'll do 3 tests, first with DNS-over-HTTPS in the browser, second with system-wide DNS-over-TLS and DNSSEC, and finally by disabling DNS-over-HTTPS in the browser to see how the system-wide DNS-over-TLS takes over. For this test, I will capture DNS traffic using TCP-dump, and then visit a website in Firefox with DNS-over-HTTPS enabled. Afterwards, I will feed the TCP-dump output to an AI assistant to analyze the result. First, I will flush the systemd DNS cache. This makes sure no previous DNS lookups are stored, so our TCP-dump capture will only show fresh queries from this test. Next, I will switch into the tests directory. I have created this directory beforehand to keep all my TCP-dump output files organized in one place. I will use TCP-dump to capture DNS traffic from the network. This lets us see exactly how DNS queries are being sent and received in real time. Here I specify -i any, which tells TCP-dump to listen on all network interfaces so I do not miss any DNS traffic. Next, I add -n. This prevents TCP-dump from resolving IP addresses into hostnames, keeping the output raw and faster to read. Then -v for maximum verbosity, so we get as much detail as possible in the capture. Next, -c80, which limits the capture to 80 packets. This avoids generating huge files and keeps things manageable for analysis. Now the port filters, I am capturing only packets on port 53, 853, or 443. These correspond to traditional DNS without encryption, DNS-over-TLS, and DNS-over-HTTPS, respectively. Finally, I redirect the output into a file, making sure both normal output and error messages go into the same place. I will not press enter just yet because I do not want to start capturing until I am ready. First, I will switch to Firefox and type my own website, sysguides.com, as an example. You can test with any other website as well. I will not hit enter yet. I will switch back to the terminal and press enter to start TCP dump, and then quickly return to the browser and load the website as well. I do it this way because I'm only capturing 80 packets, and I want to make sure TCP dump records the traffic from the very start of the request. The website has now loaded, and TCP dump has finished capturing the packets. We now have a complete snapshot of the DNS traffic generated by this visit. Next, I will open the tests directory and open a text file that I have already prepared as a prompt for the AI assistant. This is the text prompt I have created to analyze the TCP dump output. I will be using this same prompt for all 3 tests, and I will also put it in the video description so you can try it yourself. Now I will open the TCP dump output file, select all content, copy it, and paste it here into the placeholder for analysis. Now I will select all in this file and copy it. I am using Claude AI here, but you can use any AI chat assistant you are comfortable with for this analysis. I will paste the text prompt into Claude AI and press enter. Let it analyze the TCP dump output and give us a detailed explanation of what happened during this test. As you can see here, it confirms that DoH was used with multiple connections to Quad9 DoH endpoints. Here, it also shows connections to port 853, which confirms that Quad9's DoT was active as well. As you can see, there was no traffic on the standard plaintext DNS port 53, so no DNS leaks occurred. This line may look confusing at first. Since both DoH and DoT encrypt the DNS queries, we cannot see the actual DNS message contents that would show DNSSEC related flags and records. However, DNSSEC validation is happening on the resolver side, as Quad9 supports DNSSEC. In the next test, I will show you exactly how DNSSEC is validated on the system, but for now, you can rest assured that in this test, DNSSEC is indeed active and working. As you can see here, the DNS servers contacted were indeed the Quad9 servers we had set up, confirming that our configuration is correct. And here's the summary. Test 1 was successful. All DNS traffic was encrypted, no plaintext leaks were detected, DNSSEC is active, and the queries went to the correct resolver. Now, let us move on to Test 2, checking system-wide DNS using DNS-over-TLS and DNSSEC right from the terminal. In this test, I will run a dig query directly from the terminal. Our system is already configured to use DNS-over-TLS with DNSSEC enabled, so all DNS traffic should be encrypted and validated. I will run TCP dump again to capture DNS traffic, this time saving it as output 2. I will flush the system dissolver cache once more, just to make sure we get fresh DNS results, and that no old cached entries interfere with the test. Now I will run the dig command. This option tells dig to request DNSSEC information, so we can see if the response is validated and secure. This one formats the output neatly across multiple lines, making it easier to read. Finally, sysguides.com is the domain we are testing. I will press enter to start TCP dump capturing the traffic, and then press enter to run the dig query. And here is the output of our dig query. If you look at the header flags, you will notice the AD flag, which stands for authenticated data. This means our system-wide resolver has successfully validated DNSSEC for this domain. You will also see the RRSIG records, which are resource record signatures, in the answer section. These are the cryptographic signatures that prove the authenticity of the DNS response. Combined with the AD flag and these RRSIG records, they together confirm that DNSSEC is active and our system-wide queries are being validated properly. This is a key part of secure DNS. I had set TCP dump to capture 80 packets, but it turns out the DIG query did not generate that many. Since the command has already finished running, I will press Ctrl-C to stop the capture. The TCP dump output file has been successfully created. I will open the TCP dump capture file. I will select all, copy it, let me change it to test2 and paste it here. Now I will select all the content from the text prompt file, copy everything, and paste it into Cloud AI. And as you can see here, it clearly says no, DoH was not used. That is expected because in this test, we are using the terminal, which relies on the system-wide DNS-over-TLS settings we configured. There is no DNS-over-HTTPS here, since that only applies to Firefox. And here it confirms, yes, DoT was used. This shows that our system-wide DNS query went through DNS-over-TLS, exactly as we configured. This means the traffic is encrypted and secure. Here, it confirms that no external plaintext DNS leak occurred. This means all system-wide DNS traffic was sent only to the configured resolver over DNS-over-TLS, and nothing was exposed in plaintext. It is another confirmation that our configuration is working perfectly. And here it confirms, yes, DNSSEC validation is clearly visible. This proves that our system-wide DNS query not only used DNS over TLS, but also successfully validated DNSSEC for the domain. Together with the AD flag and the RRSIG records we saw earlier, this ensures the integrity and authenticity of the DNS response. We can see that our system queried Quad9 using DoT on port 853, confirming encrypted DNS over TLS traffic. The local resolver is just internal communication, nothing to worry about. This is the local stub resolver used by systemd resolve D. It is basically an internal loopback address that the system uses to communicate with its own DNS service. Nothing is being sent out to the internet from this address. It is completely normal and safe. And here is the summary. As you can see, test 2 was successful. All system-wide DNS queries went to the intended resolver, DNS over TLS was used, DNSSEC validation is clearly visible, and no external plaintext leaks occurred. This confirms that our system-wide DNS configuration is working exactly as expected. So far, we have successfully tested DoH inside Firefox, and we also tested system-wide DoT with DNSSEC enabled. Both of these worked perfectly. But here is an interesting question. What happens if I turn off DoH in Firefox while still keeping system-wide DoT with DNSSEC enabled? Will the browser still have encryption? Will DNSSEC validation still work? Or will it fall back to plain insecure DNS, leaking our queries in plain text? Let us find out in test 3. In this test, I will disable DoH in Firefox while keeping system-wide DoT with DNSSEC enabled. Then I will visit the same website again and capture the DNS traffic using TCP dump. The question is, without DoH in the browser, will encryption and DNSSEC validation still protect us, Or will we see a DNS leak? Before I begin the test, I will first clear the browser history in Firefox. Next, I will flush the system resolver cache as well. This ensures that no cached DNS entries or previously visited sites interfere with the results. I will also change the output file name to output3. In the Firefox, I will disable DoH. Okay, TCP dump has finished capturing the traffic. I will open the capture file and submit it to Claude AI for analysis to see what it reveals about the DNS traffic. As you can see here, it clearly says DoH was not used. This tells us that with DoH turned off in the browser, it did not attempt any DoH queries at all. Here is the important part. Even with DoH disabled in the browser, all DNS queries are still going through our system-wide DoT setup. This means the traffic remains encrypted and secure. In other words, the browser has fully fallen back to our system-wide DoT setup exactly as we intended. Nothing was exposed in plaintext. Just like in test 1, the DNS queries are encrypted in the TCP dump capture. DNSSEC is indeed happening too, as indicated by the large UDP size in the OPT record, which shows support for DNSSEC responses. And as expected, the Quad9 DNS servers were used for the queries. So here is the final summary. Test 3 is a success, even with DoH disabled in the browser. All DNS queries went through the system-wide DoT setup, DNSSEC validation remained active, and no plaintext DNS leaks occurred. This confirms that our secure DNS configuration is working exactly as intended. Now I will set DoH back in Firefox using Quad9. This means the browser will once again start using DoH while our system-wide DoT and DNSSEC configuration remains intact. So overall, this is a very secure setup. We get encrypted DNS both at the browser level and system-wide. That wraps up our full DNS tutorial on Linux. Before you go, I would love to hear from you in the comments. Feel free to share any tips, experiences, or anything else that could help others in the community. Your comments might really help someone else. Thank you for staying till the end. I hope you enjoyed the video. Stay curious, stay secure, and I will see you in the next video.